So the next colligative property is depression in freezing point. Okay. First of all, what is freezing point? See, it is actually the temperature at which vapor pressure of the liquid becomes equal to vapor pressure of the solid. We can also say the temperature at which the liquid and solid forms are in equilibrium with each other. Okay. Now, see, when a non-volatile solute is added, to a volatile solvent, we know that the vapor pressure decreases. So even the vapor, even the freezing point also decreases because vapor pressure and the freezing point are directly proportional to each other. So vapor pressure decreases, even the freezing point also decreases. Okay. Now let us give it this way. Vapor pressure decreases. Vapor pressure of the solvent on addition of the non-volatile solute decreases. So this can be given as P naught minus P, and this of course is known as lowering of vapor pressure. Similarly, even freezing point also decreases. So this can be given as T naught F minus Tf. Freezing point of the pure solvent is more than that of the solution. Now this can be given as depression in freezing point. Represented by delta Tf. Okay. So delta Tf is equal to T naught F minus Tf. Okay. Now let us show the same graphically. Vapor pressure is taken on y-axis. Temperature on x-axis. So as usual, we get an exponential curve. Let this be for the solvent. Now consider two things here. This is a vapor pressure of the pure solvent. And this is the freezing point of the pure solvent. Now, when a non-volatile solute is added, we get this type of a curve. Say this is for solution. Okay. This is P naught. This is P. And when you consider this, this is of course TF, the freezing point of the solution. Now this difference is what is given as delta TF, depression in freezing point. Okay. See, the most interesting point here is see at the freezing point, only the solvent molecules freeze out. It can be given this way. See, this is given as frozen solvent. A very important point. Only solvent molecules freeze, not the solute. So during depression in freezing point, only the pure solvent molecules freeze, but not the solute molecule. So this is an important point. Okay. Delta TF is T naught F minus TF. T naught F is more than the TF. This is how we can show depression in freezing point graphically. Okay. See, this depression in freezing point is experimentally found to be directly proportional to the molality of the solution. So this can be given as delta TF is equal to KF into small m, where KF is a constant called molal depression constant or freezing point depression constant, or famously known as cryoscopic constant. Okay. Now this Kf can be given as, just like the Kb, even the Kf is a specific for a solvent. Let us take one example, same example, water, for which Kf is given as 1.86 Kelvin kg per mole. Kb is 0.52, Kf is 1.86. Try to remember these values. Now let us give what Kf is. See, it is R T naught F square by 1000 into Lf, where Lf is latent heat of vaporization per gram of solvent. Very important. Per gram. Now, when the same is represented per mole, it becomes R T naught F square by 1000 into delta H F by capital F. Let us use M double dash for representing the solvent. Now, this is molar enthalpy of fusion. Okay, it is per mole of the solvent. Now, how to define this Kf? Let us consider this. If the molality of the solution is 1, delta Tf becomes equal to Kf. That means the depression in freezing point observed when molality of the solution is 1 is called cryoscopic constant. Okay. Now let us give the final expression taking the same delta Tf is equal to Kf into small m. So this can be written as delta Tf is equal to Kf into molality of weight of the solute by molecular weight of the solute into 1000 by weight of the solvent. This is when Kf is given per 1000 gram of solvent. Okay. Now, when the same is given for 100 gram of solvent, then it will become this. Okay. We can observe one very important thing, what we have been observing right from the RLB. Look at this. Delta Tf, I mean depression in freezing point is inversely proportional to molecular weight of the solute. Not just this, magnitude of any colligative property is in fact inversely proportional to the molecular weight of solute. Right. Okay. Now let us go for the last colligative property, that is osmotic pressure represented by pi. Let us first see what osmosis is. Okay. Let this be the pure solvent. This be the solution. And say this is a semi-permeable membrane. You know, semi-permeable membrane is the one that allows only the solvent molecules to flow through it, but not the solute. Okay, only the solvent molecules can flow through the semi-permeable membrane. See, generally the semi-permeable membranes employed are animal membranes. Okay, like pig's bladder. You can also use the skin of egg after boiling it. These are the natural semi-permeable membranes. But these are little delicate. So a membrane made of copper ferrocyanide in the laboratory is generally used, which can actually withstand the pressures during the flow of solvent. Okay, this is man-made or artificial. Now, let me tell you what osmosis is. See, it is in fact a phenomenon in which the pure solvent flows into the solution. The solvent molecules flow from the pure solvent into the solution through the semi-permeable membrane, right? In osmosis, solvent flows from the pure solvent into solution. See, this can of course be defined in some other way. Let us take it this way. Now, suppose if this is a low concentrated solution, this is a high concentrated solution. In this case, you know the solvent flows from the low concentrated one into the high concentrated one until and unless the concentration in both the house, both the compartments becomes the same, becomes equal. So it can also be defined as a, a phenomenon in which solvent flows from a low concentrated solution into a high concentrated solution. A low concentrated one, nothing but the one that has more solvent. This will have more solvent. Whereas the high concentrated one will have less solvent. So again, it is from something which has more solvent into the one which has less solvent, right? So osmosis can be defined in two different ways. Solvent flows from the pure solvent into solution, or solvent flows from a low concentrated one, low concentrated solution into a high concentrated solution, right? But remember, SPM allows the flow of solvent molecules only, but not solute. Okay. Now, let me tell you what osmotic pressure is. See, it is actually the pressure applied on a solution, because solvent is coming into the solution. Pressure is applied on the solution in order to prevent this flow of a solvent. To stop the flow of solvent into the solution, you need to apply pressure on the solution. This pressure, what is applied on a solution to prevent the flow of a solvent into it, is osmotic pressure. Okay. Now suppose the pressure applied on the solution is more than what is required. More than what is required to stop this. More than what is required to stop or prevent the flow of solvent into the solution, then, the solvent flows in the reverse direction. That means from the solution into pure solvent, or from a high concentrated one into low concentrated one. This is when pressure applied is more than required. Then the flow of solvent will be, again it is the solvent. Again it is the solvent, but from the solution into the solvent. Or from a high concentrated solution into a low concentrated solution. This process wherein the flow of the solvent is exactly opposite. are reverse to what we normally see in the regular osmosis is called reverse osmosis. Because the flow of solvent is in the reverse direction to the normal one. You know, this RO technique, I mean the reverse osmosis process or the RO, is generally employed in the purification of water. Like the apparatus, what we see, what we normally use, say in AquaGuard, say in Kent, kind of purifiers. Water purifiers normally use this reverse osmosis technique. See, in reverse osmosis, they generally apply a pressure which is more than required on the solution. Then the solvent flows from the high concentrated one into low concentrated one. So you get pure solvent from a salty water. High concentrated one, from the high concentrated one, you actually get the pure water by demineralizing or desalining the salty water. Okay, so that is very interesting. So there are some three very important points in this. The first one is in the regular osmosis, solvent flows from a pure solvent into solution. Point number two, you can also define it as a phenomenon in which the solvent flows from the low concentrated solution into high concentrated solution till the concentration in both the halves becomes the same. Now, to prevent this, pressure has to be applied on the solution. This minimum pressure, what is being applied on the solution to prevent the flow of the solvent into the solution, is called osmotic pressure. And if a pressure more than that required is applied on the solution, you know the solvent flows in the opposite direction. This is called reverse osmosis. Reverse osmosis technique is generally employed in desalination of water. Okay.